And there we are. So this last time we finished our VM interpreter, and we didn't have an assignment for this week except for figuring out how we would, if we had to compile by hand, how we would generate code for Simplang programs that run on the virtual machine. And if we can figure out how to do that, then maybe we can figure out how to make a computer do it. So we already saw in the description of the VM how to do a few things. So, for example, we saw how to take parameters and how to call functions, and the things that we have to take care of when we do that. Namely, for example, when we call a function, we must make sure that the arguments are at the top of the stack. Then, by convention, everything that comes after that will be basically destroyed by the function that we call. So obviously, if in Simplang we call a function, we need to make our compiler generate code that puts the arguments at the top of the stack and then calls the function, and then not just have the arguments somewhere within its stack frame and then assume that the called function automatically knows where to get them from. And note that the only memory, like the only storage that we have in the VM is the stack. So obviously, the only way we can store variables that we have assigned in let or in loop or temporary results, they need to be stored on the stack. So one of the things that the compiler will have to do is to figure out where to store them on the stack. Or in other words, to assign a stack slot for each value in a way that they don't override each other. So for example, let's look at examples. I don't know, 8 queens is a long one. Do we have anything interesting here? So one approach that we could take in the compiler is, let's say we compile this function to VM code, and each time we need a stack slot, we just pick a new one. Let's walk through a few functions and see if we can translate them by hand. And let's maybe start with a simpler one, or are we going to go right away with? Yeah, let's just do Shift L. So, yeah. So in Shift L, what we get when we enter the function in the VM code, we get 2 arguments, X and A. Where are they going to be? Which slots are they going to be? X is going to be where?
Relative to the stack pointer?
Yeah, of course. Everything is always relative. that point.
-2.
Yeah. And A is going to be where?
-1.
-1. Okay. So now we have this loop. Copy that. So now we have this loop. So let's try to be as non-smart as we can, and let's ignore. So let's rewrite this function in a way that doesn't make it obvious that there's like that these two x's are kind of related. So let's rewrite this as y. Our compiler is not going to be smart. What I mean by smart is the first thing we need to do is we need to find a stack slot for y, right? Mm-hmm. A smart compiler could figure out that x, first of all, is assigned to y, and then second of all, x is not used anymore. So it could go, oh, I could make a shortcut and just use the stack slot for x to store y, right? Mm-hmm. But that requires some more complicated analysis, but we're not going to do that. We're going to make a stupid compiler. The stupid compiler doesn't know that x is not used anymore. So from the stupid compiler's perspective, somewhere down here, x might still be used, right? So y needs a new stack slot. Does that make sense?
Yeah.
Okay. So which stack slot are we going to use for y?
I would say one above.
Which is what?
Well, one. Just one.
Okay. We're not going to use $0. Like you're just keeping it empty, just in case.
I thought that. Okay, well maybe. Well, I thought that dollars, like the stack pointer, would be reserved for the return value.
No. There's no reserve slot for a return value.
Okay. Well, I guess then.
The return value of what?
Well, for example, if we just have the main function, well, okay, no, never mind.
Okay, so we're using 0.
Yeah, sure.
But now we also need to move x to that slot, right? So you need to say move $0, $, -2, right?
Mm-hmm.
Okay. And this is instruction 0. Now, what are we going to use for I?
$1.
Okay. So now we need to set $1 to 0. All right. Now we have an if. How are we going to implement that? Jump if 0? Jump if what? If what 0?
If like that thing is 0, like.
Which thing?
Well, I guess, okay. First, you have to evaluate the expression.
Okay.
Of the condition.
So first we have to evaluate this expression, right?
Mm-hmm.
How do we do that?
Less equal? Wait. Sorry.
There's a less than, right?
Less than, yeah.
We need a target slot here. Where are we going to put the result?
In $2.
Okay, $2. So we can say I is less than A is in $2. I is in 1 and A is in -1. Right? That's instruction number 2. And now what are we going to do? Now we need to act on that Boolean variable.
So it's true if slot number 2 is not 0.
Correct.
So if it is 0, we do the else part.
Yes.
So okay, so we do 1 second, jump if 0.
0. What is 0?
Oh no, wait. First one was...
$2. Yeah.
Oh, okay. So
but then where do we jump?
Okay, so we have to write the instruction for the else part first.
Yeah. Okay. Actually, we have to write the instructions for the then part first. Then we know where the else part begins.
Yeah.
Because here we need to jump to the else. Okay.
So in 4 we do.
But now we recur. Now, what does recur mean?
It's a call function.
Really? Which
sorry.
are you calling?
We're calling the for function. My bad. So we're just jumping back.
Right.
Before we do that, we have to evaluate the expression.
Okay. So first of all, but where are we jumping to?
To instruction number. We don't have an instruction number for that.
No, we do.
Oh,
Really?
0. 0 then.
0?
No. Well, 1.
Then we reassign.
Oh no. We have to jump 2. Jump to 2.
Yes. The 2 is the first instruction of the body of the loop. If we jump to 0, then we reassign these variables. Then we reassign x to y and we reassign 0 to I.
Right.
The whole point of recur is that you do a new assignment of those variables and then you reevaluate the body, right? So, but what do we need to do before that? We need to reassign these variables.
So we know in which slot they are, and we just have to calculate the answers to those.
Okay. So how do we calculate this answer?
First, we have to set a separate slot to 2.
Okay. For which slot do we set to 2?
So one we didn't use until now. I guess $3 then, or can we just use $2?
Yes. If we have a smart compiler. I mean, it all depends on how smart your compiler is, right? If your compiler is smart enough to keep track of the fact that this was a temporary expression that now you don't need anymore, right?
Yeah.
Then you can reuse it.
But we aren't smart.
I mean, it depends. You can write a compiler. This is not that much work. This is not as difficult as figuring out that we don't need X anymore, for example. That's a little more complex.
Okay.
So sure, let's say we're smart enough in this case. So we're setting $2 to what?
2.
2, sure. And then we do what?
So
we multiply.
Right. To
where do we store the result?
$0.
$0.
Because
$0 holds y.
Yeah.
So mind you, this expression here could be plus y.
dang it.
Right. So again, if your compiler is smart enough, and you go, oh, I'm reassigning y, so I'm going to check whether y is used in the later reassignments, and I see that it's not, so I'm going to reuse it.
Mhm.
But so let's say we're not that smart. So let's put it into a new temporary one. And depending on how smartly you do the keeping track of which register is used, you could know that you can use $2. Maybe you don't know you can use $2. This is, again, a little bit more complicated. Because you know that you need $2 inside the expression, but you don't need it at the end. So let's say we're not smart enough. We're going to put it into $3. So we're multiplying y, which is in 0, with $2. Okay.
Mm-hmm.
By the way, if your compiler is smart in other ways, you could instead generate the instruction add $3, $0, $0. Because y times 2 is y plus y.
I think my screen just froze.
Oh.
Oh, no, that's okay. Now it's moving again.
So there's many opportunities to be smart in a compiler.
Do times 2 get, like in C, does it get compiled to a shift or something?
Usually, yeah. Or it might be an add. It also very much depends on, so on x86, there's this instruction called LEA.
Move the address.
It's called load effective address. And what LEA actually does is you can add 2 registers. So it's register 1 plus register 2 times a multiplier, which can be, I think, 1, 2, 4, and on x64, maybe 8, maybe in 16, I don't know. So if you had an instruction x equals x plus y times 4, you could compile this to one LEA instruction. Right? Okay. Where were we? Okay, so we have this one. So now in $3, we have the new value for y. What do we do with it?
Right now, nothing.
Aha, because
we have to evaluate the other.
Yeah,
first.
because again, y might be used in here. We don't know. Our compiler is not smart enough. So now we evaluate I plus 1, which we do how?
So just the same way, we set 1 to $2. Oh, well, $2 to 1.
Then so this is 6, 7, and then we add
to $4.
$4 because $3 is needed, and I is $1, and 1 is $2. Okay, and now what do we do?
Now we just move those 2 values to the.
Okay, so we move what to where?
Y is at 0.
Is it 0?
And we want it from $3. Yeah. And then
And here we do $1 and $4, right?
Okay.
And now what do we do?
We jump to 2. We jump to 2.
Jump to 2, correct. And now we can do the else. And else is just y, which means what? Oh, 3?
Oh, sorry. Just return 0.
Return $0. And now we know where to jump to.
Okay,
Jump
so
at 0. We need to 11. Now you will have to do this kind of backpatching in the compiler too. Right? You'll generate this code, but then you won't know, oh, where do I have to jump to? So you generate that code first, and then that one, and maybe at the end you will backpatch, or maybe in between you will backpatch. If you're super, super lazy, you can call your compiler to generate code for the then branch, but then just throw it away, just so you know how long it is. But then, of course, you need to make your compiler so it doesn't have any side effects and stuff. So you need to be not lazy in other ways. But how about we check whether this code actually works? Let's call that shiftle.sbc. Oh. Jump if greater. Well, you're not supposed to see that. So this should still run. I hope this will still run the SBC, and we want to shift 10 by 2, let's say. Ta-da! We wrote correct code.
Hey.
Okay, let's look back at 8 queens, and let's see, with the knowledge that we've gained from doing this, whether there's anything here that we don't know how to do. This looks scary, but
loading functions.
Loading functions.
All right. I guess for each one of these functions, basically you just start a new definition, like shift-L : and then you generate the code for that, and then I guess what I'm trying to figure out is where you're storing all of these instructions. Or
which instructions?
Well, I think like if you
okay, never mind.
I think like if you have 5 or 6 functions and you call it somewhere, how you figure out in the compiler where the section starts of the function.
So in Simplang, you can only call a function. You can only call the same function or a function that has been defined above. So if you compile one function after the next, then you should already know where that function starts that is being called.
Yeah.
Is that?
But it's like in the loop or the if statement, what you mentioned with the jump if 0, and we don't know where to jump if it is actually 0. In that case, we want to jump to a function, but we don't know yet where the function is actually located in which line. So we kind of have
call, and then
remember all that.
Call, look up where that function is, or the instructions for that function is. Or
I'm not sure I understand the scenario you're talking about.
Let's say you're calling shift-L
from
some loop in a different function.
Yes.
You need to, I guess it's just like generating the code is one thing, but then actually, I guess, loading the instructions for the shift within that loop in another function.
Wait. If we're compiling mask extract here, right?
Mm-hmm.
When we're compiling the call to shift L, we're not loading instructions of shift L. We're just calling to the instruction where shift L begins.
Yeah, so then I'm not sure what the call looks like, or how do I know where the instruction for shift L is?
Well, you've already compiled shift L,
Right.
so you know where it starts.
Okay.
I thought.
Does that not make sense?
I thought the functions in Simplang didn't have to be in order.
No, they do.
They do. Okay.
Yeah.
Oh, got confused there.
I'm pretty sure at this point I have that in the. Functions can only be used in their own definitions or in later definitions.
Okay. Take it back.
So let's maybe.
But so if we get to the main function in the end, do we just put that part at the beginning of the compiler? Like if we compile it to the virtual machine, we just put it at the beginning.
So the trick that I used in my compiler, because I'm lazy, was to start the program with a jump to where the main function begins.
Oh, okay. Oh, that works.
I mean, you can be smarter about it. One thing that, so when a compiler generates code, like, a proper compiler, a proper compiler generates code with where the intermediate code or the assembler code that it generates has something in the form of labels, where the compiler isn't even concerned about how long those instructions are, where they begin. It just puts that label in there, and then the assembler, which generates the machine code from the assembly language, resolves those jumps. But essentially, you would have to have a table or something that keeps track of which instructions begin where, right? Some form of marker.
Yeah.
So if you accumulate instructions in your program, you could have an optional name for each instruction that obviously doesn't get written out to the machine code, to the SBC file. But the instruction name could be, in the case of a function, the name of the function. And then a call instruction would call not to a number but to a name. And then when you're done reordering your functions in whichever way you want, you would have to make a last pass over everything where you figure out, oh, the instruction with the name 8 queens is actually instruction number 48. Whenever a call refers to 8 queens, I need to put 48 in there. Right?
Okay. Yeah.
But Simplang is made simply enough so that you don't actually have to do that if you don't desperately want to. Like the only real thing where you have to do this form of backpatching is in the if-else.
Right. Mm-hmm.
In which case it's relatively simple. It's not much overhead. And you can do it right where you're compiling the if, right? It doesn't have to be a pass afterwards or anything. I wonder whether there's some function shift L that calls shift L, let shift L, shift R. Shift R maybe.
I was going to say mask extract.
Oh, we have bit set. Oh, damn. Okay, what's mask extract? Where do you see that?
It was in. Oh, you're talking about a different SR or something like that. It's
Where did you see that?
in 8 Queens.
Oh no, but that also requires other stuff. What else might there be? Min arith. I don't know what that is. Div. No, I don't want to implement div. Whatever. Let's implement shift R. So we already have shift L. Let's implement bitset. Bitset.sbc. Okay. So we should be a little quicker this time. So X is where? I is where? -1. Okay. This time we can be smarter. Let's just be smarter. Let's be a smart compiler. So X is X, right? I is I, which means that we don't actually have to do anything. We can just keep them there, right? If I is less than 63, so what we need to do is set 0 to 63. We're just going to override it right away. Actually, less than -1, 0, right? And then jump if 0. If 0 is 0, we jump to the else. Now we don't need 0 anymore. We can reuse 0 here. Actually, no. We're just gonna do the add trick. Also, we're gonna use the fact that we don't need X in the right hand side anymore. So we're just gonna say add -2, -2, -2. Does that make sense? Yes?
Yeah.
That looks neat.
That
looks neat. So.
Yeah. 5 add -1, -1, 0. Correct?
And then we can jump to 0 again.
Correct. We can jump to 0. Else X is less than 0. We can reuse $0. So we're going to say less than X is what? -2? Oh, but we need 0. Also, this would be 0. And also, we need to set 0 to 0.
X is -2.
X is -2? Yeah, X is -2. Okay. Less than 0. And then we can return that. 9, return 0. Will that work?
The else.
Oh, yeah. 2, 7. Is it going to work? Yes, no?
Yes.
You're very confident.
Not always.
Bitset. bit set SBC. So let's say 10, 0. What should the result be? 10, 1, 2,
0. Oh, it's
3,
1.
4.
All
All right. All the rest are 0. Boom. So, and now we're going to do the Shift R. But to do that, now we need to do a stupid thing, which is Shift R.SBC. We need to take these two functions. So this is bit set. But then we need to use Shift L. But this one, it doesn't compose, right? Because we have this jump here. But so the nice thing is, so we need to adjust these, right? We need to adjust the jump of 0, and we need to adjust the jump.
Mm-hmm.
Yes?
Yeah.
Mm-hmm.
And ideally the instructions on the left.
And the instruction numbers. But the nice thing is that the first instruction is number 10 instead of number 0. So we can just append a 1 here and make this 2. And then the jump are 21 and 12. So this is Shift L. Shift L is 10. Bit set is 0. And now let's implement Shift R. M.
But then do we have to include a jump instruction at the beginning to start a Shift R?
Oh no.
Oh god, I'm sorry.
You're right, we do. You're right, we do.
Are we just? Oh no. Oh well, we can just put the function at the beginning. Oh no, wait, that's not better. Okay, sorry. Damn it.
Doesn't Emacs have like a marked rectangle?
No, we can't. No, that's not gonna help us. Oh, that's not what I wanted to do. Does Emacs not have a what?
I was going to say a marked rectangle that you can use to cut and maybe paste.
Yeah, that's what I was going to do. I'm sure there's a trick for yeah, see, that's the ugly thing then.
Whoa.
Jump. So we're jumping to Shift R right here.
Mm-hmm.
But now we need to adjust every other jump because this is 1 more now. So this is 8. This is 1. 1?
Wait, not.
Wait, how?
3? No, 3, right?
Oh, that was the bit set. That was the bit set. 22.
Oh, okay.
13. Okay. Now, just so that we remember, this is Shift. This is bit set, and 11 is Shift L. Okay. So Shift R. We have X in
-2.
and we have A in -1. Okay. So now we need new variables for these, right? These are completely new. So we need new stack slots. These are completely new variables, and we're going to use X and A within the loop. So we're going to put R in 0. 23 set 0 to 0. And we're going to put I in 1. 24 set 1 to 0. Oof. What?
The screen keeps freezing.
Oh.
I don't know if it's.
Are you back?
My Wi-Fi. Yeah, it's back again.
Okay. So let's add a plus I first into $2. A is -1 and I is 1. By the way, you really need to pay attention because I'm probably going to make mistakes. Oh, see, already I made a mistake. You didn't spot it.
I was just about to say that.
Okay, so we need another temporary one where we put 64 in, and then we do less. Is it less than? Less than, yes.
Mm-hmm.
We can reuse this. So 2 and 3 we don't need anymore. We're going to use 2. So now if this were a more complicated program, I would actually have to keep track of, I'm using $2, I'm using $3, which one can I use next? Right? I have to write it down somewhere. So obviously, your compiler is going to have to write it down too. Less than, unless you want to go the absolute minimal route of just using the next slot, like not even keeping availability of slots, just always incrementing slot number, right? But then you're going to end up with with way more slots than you would have to use, which will actually, on the one hand, limit your recursion depth, but on the other hand, it might actually make your program slower because of stack effects, because of cache, because of cache size, right? So the smaller your working set, the better it is for making the program run faster.
Okay.
So less than 2 and 3. Yes?
Mm-hmm.
A jump if $2 else. Okay, here we are recurring. Whew. Now, how do we implement this? We have a nested function invocation, right? So we're calling shift L with the result of bit set.
Yeah, so we have to evaluate this from the innermost thing out.
Right.
So you need to do a plus I again.
Oh, so actually, how about we are super smart, and we realize that we can reuse a plus I in here, right? So this is a plus I, $2.
But we overrode it in 27, right?
Yes. To set the less than to 3, and then dump it.
What were you saying?
In line 27, we were overriding the result from a plus I, so we would have to use a different slot for that.
Yeah, that's what I'm saying.
Oh, sorry.
We can use a different slot here. Okay, but now here comes the more complicated part. So let's actually write it in the stupid way first. So let's use, I don't know, whatever, $3 here. So in $2 we have a plus I. Okay.
Mm-hmm.
So we have the arguments in stack slots. We have X in a slot. We have a plus I in a slot. But that's not enough to call the function. What do we need to do to call the function?
So we need to
the variables onto. You have to set like you have to set like we'll say or you already have.
We can use 3.
Okay, yes, you have to set. What you already know 2 is. is in, wait, where is it? A plus, oh yeah, it's right there. So it's into, you have to move -2 to, oh, you have to move 2 first. You have to move $2 to 3, or you could do it to 4. Yeah, just to make it a little simpler. Move $2 to $4, then $-2 to $3, then call.
No, the other way around. If X is in $3, then A plus I must be in $4.
Yeah, that's what he said.
Oh, that is what he said. Okay. Okay, so we're moving X, sorry, into $3 from X. And we're moving into 4, $2. This is A plus I. So now these two are our topmost stack elements, right?
Mm-hmm.
And you have to call with, like, basically, does call take a slot number?
Call takes, what does call take first? Call, oh, come on. Oh, sorry. Yeah, so the instruction first. So the instruction is, it's bit set. So bit set is at 1. And now by how much do we move the value stack pointer?
So by 5.
Yes. Because $4 needs to be at -1 to be the second argument, or the last argument if you want, right?
Yeah.
And we want the result to be where?
So we can just override. Can we override anything? $3?
We can override 3. So the thing is that this result is the first argument to the shift-L function call.
So you might as well do 3.
So we might as well use 3 and 4 again. Right?
On that case, just, oh, yeah. Mm-hmm, mm-hmm.
Then you do call shift or move. What is I?
4. Oh, I is 0? No, I is 1.
And then call. First, is that 11?
11? Yes. So same thing, 5, because same number of arguments. And the result in 3? Do we care?
We don't care.
No, we don't care.
So now I could be super, super, super smart. And I could have foreseen that I'm going to use A plus I as the second argument here. Right?
And put it into 4 to begin with. And then just move.
And put it into 4 to begin with. But actually what I can do, I can put it into 3 and then use $2 here. And then use $2 and A plus I is in 3 and 2. This is a plus I less than 64. And now I'm going to use the stack slots because I don't need 2 anymore, right? Mm-hmm. So I can use 2 for x and 3 for a plus I, which is where it is already. So I don't have to do this. And I can use 4 here. And then this goes into 2 again, and then this goes into 3, and then this is 4 again. No, these are not dollars.
Oh, okay.
These don't refer to stack slots.
Oh, okay. I see.
And then this goes into 2.
I see.
Mm-hmm.
So we saved 1 instruction, at least.
That's like in version 3.0.
Come again?
We'll implement that in our compiler in version 3.0 or something.
Yeah, maybe.
Looks cool.
Now, our compiler would actually do the left-hand side of this. I mean, depending. Our compiler could be smart enough to realize that it doesn't need to copy R to a temporary slot because it's just R and it's just where it is. But maybe it's not that smart. It depends on how smart it is. But anyway, what we need to do is now we need to add R to our result here, $2, right? And the result needs to be in R again. So we can just add 2 to R because we don't need R here.
Yeah.
Right?
Mm-hmm.
Felix?
I'm here. Can you hear me?
Yes. Do you follow?
Yeah, I follow.
So we're adding 2 R. So we're adding R plus the result of what we just did of the shift L, and we're saving it in R. And then we just need to do I plus 1. So we're going to say set $2 to 1 and add $1, $1, and $2. I equals I plus 1. And then we jump. Hooray. 2, where?
25.
Here we return R. So this is 37. Return $0, which means that this goes to 37. And it means that we're done. Is this going to work?
Well, I'm a little less hopeful, but I say yes.
I don't think this is going to work. This is too smart. Too smart for its own good. Okay, did we number correctly? 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4, 5, 6, 7. 7. Okay, also, the shift R now starts at 23. This is 23.
Okay.
Let's try this. Shift R, SBC. Okay, 10 by 1, what's the result? We're shifting right by 1 bit.
Oh,
10 divided by 2 is 4. 4 times.
What, 5?
Oh, no, 4.
Come on.
Sorry, it's 5.
Okay.
4.
Huzzah! Triumph of the intellect. Okay, if you shift by 2, what's it going to be?
No, then it's going to be 2. Sorry.
Whew, man.
Man.
So there we go. All right. So at this point, is there anything in this thing that you feel like you couldn't translate?
Well, I think the only structure we didn't mention is just the other let expression in the let, like in the functions, but I think they're not
Sure,
too
but
hard.
the let is just like a loop without a recur.
Yeah, right. Yeah, no, I think that's
Right.
okay. Mm-hmm.
You do understand that?
Yeah, sure.
Yeah.
No, that's not too hard.
So there's other like very simple smart things that you can do in the compiler, like for example, expression that's a plus minus 1. What I can do is, that's a very simple optimization, which is called constant folding. Constant folding just means that if it finds an expression that is a constant, it just evaluates it. So -1, for example, even though it's the operator minus and the number 1, right? It's not an integer literal composite expression, but it always evaluates to a constant, -1. It could just replace it with the number -1. Right? So a very stupid compiler would first load the number 1, and then it would negate it, and then it would do the add.
Yeah.
So now, fun fact, you can actually do this in your syntax tree and even speed up the interpreter.
But so would you, like, let's say you had a plus or minus, plus -1 plus 3 plus 4 times 5, then you would evaluate all of those constants first, and then like
well, so here's the thing. That's a little bit more complicated because let's say I have a plus 1 plus 2 plus 3, right? The way our grammar works, this turns out to be a plus 1, and that plus 2, and that plus 3.
Yeah.
There is not a single. If you do naive constant folding, you're not going to figure out that the 1 and the 2 and the 3 can be grouped together. Right? You would have to do some form of normalization of expressions, which would, for example, take a long chain of additions and reorder it so that all the variables are at the beginning, for example. And then you could even order by which kinds of variables they are, because the expression could be a plus 1 plus 2 plus 3 plus a plus 4 plus a plus 5 plus a, right? Or plus b. If your compiler is super smart and it does a normalization of this expression, it would go, oh, I'm going to do the a's first. So I'm going to do a plus a, and then I'm going to do the b's. There's one b, and then I'm going to do 1 plus 3 plus 2 plus 3 plus 4 plus 5, and then it would go, oh, this is a constant, so I'm going to fold this and put in the result. And now I know that this is a, which I can replace with a times 3. If you have time, if you want to implement that, go ahead.
Could make a competition out of this.
Well, there are actually, so in none of the code, you wouldn't write code like this in Simplang, right? Nobody writes code like this. where code like this comes in is as a result of other optimizations. So for example, one optimization would be inlining as well as like specialization of functions. So for example, let's say in 8 queens, do we have that somewhere? So here, for example, we have a mask extract where the third argument is a constant. We could use this fact and specialize the mask extract function. So we could either inline it, right? Which inlining just means I'm taking this whole thing, I'm putting it in here, and I'm replacing the arguments here, x and s and a. Basically, I'm making one let before that, right?
Mm-hmm.
And then you can go and you. Okay, so maybe I should show you. Let's say I'm actually doing this. Queen. Here. Let's say I inline this here, which means what I'm actually doing is I'm first making a let that says x equals board and s equals x plus x times 4 and what is it? A equals 4 in this thing. Right? This is semantically equivalent to the code from before.
Mm-hmm.
Do you believe that?
Looks good to me.
Yeah. So now you could go, oh, but A is 4 here in this let. So I could just replace the occurrences of A in here with 4s. Right? I'm just going to go A equals 4. And then, of course, here I can't replace it. I can't replace it in here because this is a different A, right? This is a counter in the loop.
Yeah.
So now I've gotten rid of this. This is gone. And now what I could do actually is I could do loop unrolling, because I figure out, my compiler is really smart. It knows that I'm using A as the counter in the loop here. I'm decrementing it here by 1. And I'm setting it to 4 here. So I can unroll the whole body of the loop 4 times.
Ooh, yeah.
Which means what I'm doing is I'm starting off this. This is what I'm starting off as. Now I'm putting this in here. This is the first unrolling. Where A is 4. 4. And now I need to replace the recur with the second unrolling, which means I'm taking this whole thing and I'm putting it here. But this is X now. This is R now. And A is 3.
I think you assigned to the wrong side for the R.
Oh, what did I do?
Right there.
Yeah. So this is 3. Else recur. Oh, this is the recur. Right, so I got 2 more to go. I'm almost done. And so I'm putting this here. Again, this is the loop body. I'm putting it in here instead of this recur. But now, again, I have x equals that times 2, blah, blah, blah. And this is 2. Now I need to do it again. Oh, except that also here. I mean, sure, we don't need this anymore. This is the one that we're replacing. So here, do it again. Now it's 1. Now I'm going to do it again. And now it's 0. And here it's true. Right? And now also note that here, this is false. Right? So now our constant folder goes, oh, 3 is not 0. So this is false. So if I have an if where the condition is false, then obviously I can delete the whole if and just replace it with the consequent. Right?
Yeah.
In here. Same here. And here it's the same thing, except that here I replace it with the
with the else. With the other thing.
With the consequent. Yeah, and here same thing. So this is gone. And R starts out as 0. So I might be smart enough to replace shit here. Like I can go, oh, 0 times 2 is actually just 0. And so this is x less than 0. Really? Plus x less than 0? Interesting. But now note that there's no conditions here anymore. Right? I've done this whole thing. And I've done all this constant folding stuff and removing conditions and loop unrolling. And I don't have any ifs anymore. And I'm sure there's more optimizations that you can do on this.
Do people tend to like? Does it ever happen where you look at all the constants within the function and then put them in slots like 0 through 5 or whatever, so then I don't have to keep reassigning those guys?
Yeah, sure. Yeah, you can do that too. So if you know that, for example, that you're going to need the number 4 very often, or 0 here, or 2, right? Your compiler might be smart enough to figure out, oh, you know what? I'm just going to reserve a slot at the beginning of the function and put 2 into it. You might even be smart. Oh, well, no, that doesn't actually work. Never mind.
There's something I did. Sorry. There's something I did in my project where I try to differentiate between relative slots and the absolute values. So if it's if there's a dollar sign, then it's a slot, and if it's not a dollar sign, then it's a value. Is there a?
That could also be an instruction, though.
Is there like also on the assembly language? Is there? I never programmed in assembly before, but are there also constants you can just put in to add functions and such? So that would be like easy to.
Well, there's no functions in assembly.
Like no, I mean like instructions.
So,
Instructions.
but wait, so what you're saying is you extended the virtual machine to make it possible to also allow constants everywhere.
Yeah.
If you wanted to, so you could say add $0 is $1 plus 5, for example.
Yeah. Right.
Yeah. So this is you've extended the virtual machine.
Okay. Mm-hmm.
It's not the same virtual machine anymore.
Dang it.
Right.
Okay. Yeah. Yeah. Right.
But so this is another thing that we would have talked about. This is obviously something that you would do to make something that you could do to make the program run even faster, because now you're saving one instruction by allowing immediates inside the instructions.
Yeah.
So that's totally permissible if you're designing virtual machines. But still, there's a trade-off. Like you still, if you do it for every instruction in every argument slot, then you need to have, there's some kind of overhead that comes with it, right?
Right.
Because you need to know, oh, do I have a constant or do I have a slot? Do I need to get it from here, or do I just copy it over there? So you're adding a little bit of a cost to each instruction, and it might not be worth it.
Why not just make it a new name?
Yeah, that's the other thing that you can do. So I actually did an extended virtual machine where I added the most used, where I had an add immediate or add im, I think, right? Which would look like this. So now it's a new instruction.
Mm-hmm.
So now the overhead comes in the cost of adding a new instruction, which is probably less than the cost of, because for looking up the instruction, you need to do some kind of a lookup anyway, right? It's probably a jump table that you'll have. So if the jump table is a few entries longer, doesn't really make much of a difference. But there's no additional overhead for each instruction. But still, there's a limit. Like you can't add 100,000 instructions to cover all your bases without some overhead.
Yeah.
If worst comes to worst, you're gonna blow the size of your cache with just the code for your virtual machine, which is not good. But your question was about assembly. So in assembly, you can't just make shit up, right? You can't just, if an instruction always takes a register, you can't just pass a constant there, right? That's not how it works.
Okay. Yeah.
Even if you might want it.
I didn't really program in assembly, so I wasn't sure if that was even possible.
Yeah, we'll at some point we'll have to talk about assembly too, obviously, and different assembly languages are, have different ways of doing things. Like in x86, usually for the second argument you can put in a constant if you want. Like most instructions support that. Most RISC machines don't have that. They only have it for some instructions. Some of them don't have it at all. So on the Alpha, for example, all of those arithmetic instructions, they're always just register and register. Mm-hmm. And if you want a constant in a register, then you have to use a separate instruction to get that from somewhere. All right. So for the next assignment. Oh, it's been a lot of time. Where's the assignments? But this is pretty easy, especially considering that you're going to have 2 weeks to do it. We want a compiler for programs that has a main function and that either returns an integer literal or one of the arguments. Right?
Mm-hmm.
You already have the parser, you have the syntax tree. You don't need to worry about that. Just produce the VM code. Cool?
Cool.
All right. Then we'll talk in 2 weeks.
All right. Thank you.
See ya.
Bye.